Now that we know what is starch and damaged starch and why it is so important, we are going to talk about how we can determine the starch content. So there are multiple methods, but the official method is AACC method that we are going to talk about. And AACC is American Association of Cereal Chemists method, and then the AOAC method number is different, but they are the same method. And this is a spectrophotometry based colorimetric method. And the idea behind the principle of the method is we gelatinize starch, and then the starch is hydrolyzed with thermostable alpha amylase and converted to glucose using the amyloglucosidase. And then we actually measure how much glucose is released using a glucose peroxidase reagent. And there is the pink color formation, and then we measure the intensity of the pink color formation. So stronger the color, that means there is more starch, and using the curves, standard curves, we can actually quantify how much starch we have in the sample. And this is again the principal idea behind the total starch assay. This is the AACC method. So starch is partially hydrolyzed with alpha amylase, heat stable alpha amylase. And then we have treatment of another alpha amylase, is amyloglucosidase. And amyloglucosidase is actually hydrolyzing all the starch, including the branching points, to glucose. And then the glucose is quantified with glucooxidase assay, chemical-based assay. And then again, we measure this pink color formation using a spectrophotometer. And we calculate the starch content using the formulation. And we are using the Megazyme kits, but there are other companies providing kits for total starch assay. Now I'm going to talk briefly about the lipids. So lipids are the minor constituents of the cereal grains and concentrated in the bran and germ. Again, when we talk about grain chemistry quality, the most studied molecules are proteins and then carbohydrates and starch, but there is even relatively less research on wheat lipids. So there is a variation how much lipids we have in different cereals, and this table is showing the minimum and highest ratios for different cereals. And if we look at here, wheat lipids are changing from 1.4 to 3.5%. But for some other grains, it can be up to even 13.8% for corn. And then even in oat, it could be 11.6%. So lipids are covering a wide range of compounds, and they are in soluble water, and they will be soluble in organic solvents. So most universal lipid extraction solvent is hexane. And then they will be containing long-chain hydrocarbon groups. And there are non-starch lipids and starch lipids. So there are some lipids, they are part of the granular structure. So for wheat flour lipids, if you look at them, again, most of the lipid is located in the germ, 8 to 15%. About 6% of them are located in bran. We only have 1 to 2% in endosperm. And then again, this table shows more in-depth location of lipids. In the straight is 1.6 in this example. Clear flour, because it's closer to bran, it has higher ratio. And germ mass here is 15%. So highest lipid content is in the germ than bran. This is why it is very important to stabilize them for whole wheat flour applications. And then we can have different types of lipids, and in terms of they are free lipid or bound lipid, and then their distribution in different meal fractions. Again, for experimental meal, if you look at them, free lipids in total is 63.7, and then free lipids is going to be 1.48, and most of the lipids, again, they will be in this table. We see that bran has the highest percentage. I guess in this chart, this is from 1960s, that we don't have a separate location for germ, but then we see the first reduction. Again, we see higher ratio of free lipids. If you look at individual fatty acids and what we have in the milled products, Let's put the emphasis on flour. This is the flour we generate from endosperm. This is the one most wide range of applications we have. The most commonly found lipid is the linoleic acid here. We see that it's the 0.65% linoleic acid. Again, it's one of the highest ones in the brand as well. So linoleic acid, the most dominant lipid we found, fatty acid we have in the wheat flour. There are again different types of lipids. We have fatty acids, we just talked about them, and then acylglycerols, phosphoglycerides, glycolipids, sterol and tocopherols and carotenoids. They have relatively less relative abundance and functionality in baking systems. But for the wheat flour lipids, starch lipids are about 1%, and then most of them are polar lipids. And then for non-starch lipids, the most of them are also non-polar lipids, and they are made of triacylglycerides and free fatty acids, and then phospholipids and glycolipids will be the polar lipids we have in the flours. So why they are important? Because the oxidation process, or lipid hydrolysis or lipid oxidation, because they develop flavors and the volatile odor compounds. And especially again high lipid compounds, if they are exposed to light and relatively humid and high temperature conditions, they are going to have faster conversion of lipid oxidation. And storage at low temperature and low moisture is going to minimize the lipid oxidation. And the lipids in milled grains are more susceptible to degradation because of exposure to light. And then whole wheat flour, again, because we have higher amounts of these lipids, they need to be controlled. So why they are important? We talked about starch earlier in the course, that amylose and the lipid complex formation is going to be very important for us to control the starch recrystallization, starch retrogradation, delaying the staling. So we add some lipid compounds to control this process. Lipid functionality, they also have important functionality in baking. And we talked about different types of lipids, but the lipids, even though they have 1 to 2% in endosperm, they have positive impact on the baking quality because they act as lubricant and they improve the gas retention. They also prevent interaction between the starch granules during gelatinization. They provide structural support and they retard water transport. So here it's a nice cartoon version again how additional lipids are helping starch protein interactions and stabilize the dough network in general. They also help with glutenin gliadin stabilization. Starch is interacting with protein molecules and the lipids are helping with those. With this, we completed the part 2 with chemistry and structure.